This lecture will be about complex numbers and is targeted for people who are pre-university. Let's say we got a quadratic equation x squared minus 5x plus 6. We know that we can factorize that into the two roots of x minus 2, or the two factors of x minus 2 and x minus 3, which gives us the two roots of x equal to 2 and x equal to 3. Now, if we look at the discriminant of quadratic, which is just b squared minus 4ac, we see that there is a positive number, indicating that there are two distinct roots to this quadratic. If we were to look at this quadratic, which is x squared minus 2x plus 1, we can factorize it into a perfect square. So that means there's one repeated root of x equal to 1. The discriminant is going to be b squared minus 4ac. In this case, it's going to be 0, so indicating there's one repeated root. What if we had the quadratic of x squared plus x plus 1, and we can't really think of any of two factors, so let's just hope for the best and put in the quadratic formula. And we see that we got a square root of a negative number. So how can we do that? We introduce an element to help us with this kind of an equation. We don't know how to square root a negative number, but what we can do is we can define something which its square is a negative number. We call this I. So the more important use of it, well, the more common use of it, is I equal to square root of minus 1. Going back to this piece, we see that we can factor it out to be, well, we can solve it to be minus 1 plus minus square root of 3i all over 2. Leaving our two roots to be and these will be our two roots. It may seem pretty useless and a bit unreasonable to consider these things in terms of I as an actual solution, but because we can define it, and because it does obey the rules of ordinary algebra, we can treat them as a legitimate item. Now, we need to see if it actually satisfies the rules of ordinary algebra: add, subtract, multiply, and divide. So, in complex numbers, we normally indicate them as a complex number is considered as z is equal to x plus I y, where x and y are themselves real numbers. So there's for every complex number, there's going to be a real part to the complex number and an imaginary tail. So if we have an actual complex number, and let's say our actual complex number is z equal to 1 plus I, and we have another complex number, let's say w equals to 1 minus square root of 2 times I. If it satisfies the ordinary rules of algebra, add, subtract, multiply, divide, then it's a legitimate thing. So let's actually work through what the addition, subtraction, multiplication, and division would be. because z is going to be 1 plus I and w is going to be 1 minus root 2I, how we actually carry out the addition would be we add the real parts because this is going to be z and this is going to be w. We add the real parts, so 1 plus 1, 2. And we add the imaginary parts, so I minus root 2I, so plus 1 minus root 2I. And that's fine. Now we will do the subtraction or the difference. Again, we simply subtract the real and the imaginary parts. One minus one is going to be 0. I minus root 2 is going to be let's move on to multiplication. If it does satisfy the ordinary rules of algebra, we should be able to do our typical expansion. So 1 times 1 is going to be 1. 1 times root 2I is going to be minus root 2I. I times 1 is going to be plus I, sorry. And I times minus root 2I. Now, here's the thing. Because we already defined I squared to be minus 1, we need to know that every time we get I squared, it's going to be minus 1. So we get a minus root 2 I squared. But I squared itself is going to be minus 1. Leaving all of this as 1 plus root 2, there's the real part. And the imaginary part is going to be 1 minus root 2I. And that's the multiplication. For the actual quotient of z divided by w, we're going to have 1 plus I all over 1 minus root 2I. However, we would always like our complex numbers to be expressed as a real part plus an imaginary part. So we somehow need to compress or simplify this fraction into a real plus imaginary. But over here we got a real plus imaginary on a real plus imaginary. So how can we do that? We need to introduce something we call the conjugate. The conjugate of a complex number. So what we do, what is a conjugate? Let's say we get a complex number called v, which is equal to a plus ib. Its conjugate denoted by v bar is going to be a minus ib. We simply just take the imaginary portion and we flip the sign. If it's plus, we go to minus. If it's minus, we go to plus. That's it. So what do we do here for this question? We multiply by w bar on w bar, which is going to be 1 plus I on 1 minus root 2I times for the denominator 1 times 1 minus root 2I times 1 minus root 1 times root 2I minus root 2I times positive root 2I. We'll simplify this later. For the numerator, 1 times 1. Moving on to the next page. And let's actually simplify all of this to become a real plus imaginary thing. So we get 1 minus root 2 plus I plus root 2i. All over. Now, minus root 2i plus root 2i, the cross terms will kind of cancel off, leaving us with 1 and minus 2i squared, but I squared is going to be plus 1. So 1 plus 2 is going to be 3. Now we can actually break this up into a real plus imaginary component to become 1 plus 1 minus root 2 on 3, that's the real part, plus 1 plus root 2 all over 3i. Much like in when we did mathematics with real numbers, we normally plotted our numbers on the number line. Now, because complex numbers have two parts to it, the real part and the imaginary part, we would like a way to visualize these complex numbers. So instead of a number line, because there's now two parts to a complex number, we're going to plot them out on something called the Argan Diagram, which is a two-dimensional plane. Using the previous examples of z's and w's, z plus w is given by that, z minus w is given by that, z times w is given by that, z divided by w is given by that. We're going to try to plot this out on the Argan diagram. Now, what is the Argan diagram? It's simply just a two-dimensional axis where all the real parts of a complex number are indicated on the horizontal axis and all the imaginary parts of a complex number are indicated on the vertical axis. Our OG z, which was 1 plus I, is going to be roughly 1, 1. So z is going to be roughly over here. Our OGW, which is going to be 1 minus root 2i, is going to be here, 1, and then root 2 somewhere here. And therefore our z plus w, which again was 2 plus 1 minus 2i, is going to be 2 and somewhere here. And our z minus w, which is 0, 1 plus root 2, is going to be 0 on the real axis, but 1 plus root 2 on the imaginary axis is going to be somewhere here. Our z times w, which is going to be 1 plus root 2 and 1 minus root 2, is going to be somewhere 1 plus root 2 and 1 minus and 1 going to be somewhere over here. And finally, our z divided by w is going to be 1 minus root 2 on 3, 1 plus root 2 on 3. So one minus root 2 on the x-axis is on the real axis is going to be here divided by 3, so somewhere here. That's the real part, and the imaginary part is going to be 1 plus root 2 1 plus root 2 divided by 3, so somewhere here. Now this would be a way to visualize the complex numbers on the Argan diagram. Incidentally, if you got two complex numbers z equal to a plus ib and z bar, which is the conjugate, is equal to a minus ib, where would they be with respect to each other on the complex plane, or other words Argan diagram? Let's assume z happens to be, let's say a and b are both positive numbers. Z happen to be here. Because z bar is just the negative, the imaginary part is just the negative of z's imaginary portion, the conjugate will simply be a reflection along the real axis. Now, with that said, we can move on to another topic where instead of expressing complex numbers as a dot on the Argan diagram, we can represent it as vectors from the origin. In this case, if z happened to be 1, 1 corresponding to the complex number 1 plus I again, z bar would have to be 1 minus 1, which corresponds to the complex number 1 minus I. Because we can represent complex numbers as a vector from the origin, we can actually make a right angle triangle out of this. And because there's a right angle triangle, we can actually use Pythagoras' theorem, where this height is 1 and this width is also 1, leaving this hypotenuse as square root of 2. So that means this complex number has a magnitude, this complex number z has a magnitude of root 2, meaning how far it is from the origin. Or if you don't like to write it that way, you can actually write it as z from 0 plus 0I, because there's the origin. Similarly, because the conjugate z bar is just the complex number z reflected about the real axis, its magnitude will also be the same. And now we see that the magnitude of z is equal to the magnitude of z bar, which is in this case going to be square root of 2. Lastly, we can actually factorize polynomials, where instead of a real number being the input of the polynomial, we have a complex number as the input of the polynomial. Now, before we carry on, we need two really important theorems in complex numbers with regards to polynomials. The first one being the fundamental theorem of algebra, which states that a polynomial of degree n has n roots, be it real or complex. Now, within this theorem of the fundamental theorem of algebra, we have something called the conjugate root theorem, which simply means that if the polynomial has all real coefficients, then any complex roots will occur in conjugate pairs. With that said, we can actually factorize this polynomial which we saw at the very start, which is pz is equal to z squared plus z plus 1. Once again, putting in the quadratic formula. Oops. Now, notice that these two roots are themselves conjugate pairs of each other. Complex roots, for some reason, are always denoted by omega. The only difference from these two roots is the plus and the minus sign from the imaginary part. So these two complex numbers are indeed conjugate roots of each other. We can actually use this fundamental theorem algebra and the conjugate root theorem to factorize what we call the cube roots of unity. Let's say we need to solve the equation z cubed equal to 1. We're just simply asking what is the cube roots of 1. You will think that the cube roots of 1 is only 1. But as what the fundamental theorem algebra says, any polynomial with degree n has n roots. So there's actually 3 roots in this, but the 2 other roots are conjugate pairs of complex numbers. We can actually factorize this. And from what we saw earlier, these 2 roots are going to be omega 1 is equal to minus half plus root 3 on 2I, and I'm going to call it omega 2 now. Instead of omega 0 and omega 1, I'm going to call it omega 1 and omega 2. And what is this one here? We call that omega 0. Now I challenge any one of you to show that the cubes of any one of these 3 satisfies this original equation. In fact, I challenge also that if you take omega 1 squared, you're going to get omega 2. If you get omega 2 squared, you're going to get omega 1. And if you get omega 0 times plus omega 1 plus omega 2, so omega 0 plus omega 1 plus omega 2, you're going to get 0. And if you take omega 0 times omega 1 times omega 2, you're going to get 1.